many different places. I think you can see here that he's also coming, visiting New York, NYU right now. So, okay.
Thank you, Avi. So, what I'd like to tell you about today is a different proof of a recent result in something called metric embedding or dimension reduction. And actually, it's not so much the result that I'd like to show you, because the result is already known. It just, we'll see a simpler, maybe more intuitive proof of it. I also like to point out that the technique used can hopefully be used in for other applications. So it's a technique that has been used before, an information theoretic technique that has been used before. It's very simple, very basic. And one of the goals here today is to show you this technique and maybe encourage you to look for other applications. Okay, so let's start, and stop me if there are any questions, because it's really supposed to be very basic. I'll give all the necessary definitions. Maybe it would be even too basic for some of you. So you'll know in a few slides. It's from a classic book called Flatland, and this depicts how how you arrange the rooms in a two-dimensional flatland. Can seem to fit with the topic of the talk. So the question this is a classical question of dimension reduction, where you have points in high-dimensional space, and you'd like to reduce the dimension while preserving some property of these points. And typically what you have are endpoints in some very high-dimensional space, say d prime dimensional space. And you'd like to map it to a much lower dimensional space, r to the d. And what typically you like to do is to preserve distances between the points. In this case, I'd like to preserve the L2 distances, the Euclidean distances between all n-2 pairs of points. Okay? So the question is, can we do that? Can we reduce the dimension? Can we find a mapping f, a function f, that maps each point to some point in much lower dimensional space in r to the d, such that the distances are preserved up to some constant factor? So I don't require to keep them exactly, but only up to a factor d. D is something we call the distortion of the embedding. It's by definition always at least 1. 1 is when there's no distortion at all. Well, it's my timer. It's my timer. I know when to switch a slide. Yeah. Okay. I have all the stock communication behind that window. If I switch now, it will be a bit embarrassing. Yeah. It's your communication too, so. Okay. So, okay, so that's the goal. That's what we'd like to do. And this is a classical question. This is pretty well understood. This question is not what I'll talk about today. The famous Johnson-Lindenschauss lemma tells us that we can indeed do that. We can reduce the dimension to as low as log n over epsilon squared, while having distortion of only 1 plus epsilon. Okay, so this is pretty good. For any set of endpoints, you can reduce their dimension to something essentially logarithmic in n, while keeping the pairwise distances up to 1 plus minus epsilon. Okay, and in fact, if you want to preserve distances exactly, you can of course do that in n-dimensional space, right? Take the span of the points and imagine the points in their span. This would be a reduction to n dimensions. But here the goal would be to go into a much lower dimension. Here, that's what we do here, go into log n dimensional space. And this is a very basic statement in this area. It's extremely useful. The applications are also computational. This area in general, if you have a set of points and you don't want to store all the points, only want to store some small information about each point, you can reduce the dimension, then you have less to store, right? It's much easier to process. Later you can answer queries in a much easier way because it's in the lower dimensional space, etc., etc. This lemma is known to be tight, result by Noga from 2003, and lots of applications, as I mentioned. So this is not the topic of my talk currently. This is about the L2 setting, which is pretty well understood. I should also say the proof is very nice. If you haven't seen it before, I highly recommend it. It's just essentially all you do is project on a random subspace of dimension log n over epsilon squared. Okay, and the proof is not difficult. You sort of do union bound of all pairs of points, and then by Chernoff bound, you can say that each pair of points is preserved. The distance is preserved with high probability. Then you only have to do union bound of all set of points. So this is something classic by now. The question we are addressing here is the L1 setting. So now we go into L1, and the situation here is far not as understood as well as the situation in L2. And let me tell you what's known about it. So it turns out that you can always reduce a dimension to n choose 2. So if I have n points, I can always reduce it to n choose 2 dimensions. This is a nice exercise, and you can do it without any distortion. Okay, so at least you can do something. Even if the dimension is extremely high, you can always go to n choose 2 dimensions, and this only involves no distortion whatsoever. Okay, but we don't want to have such a bad dependence on n. This is something like n squared. We'd like to see if we can decrease it further, and there's a result by Keith Ball from '92, where he shows that if you don't want to have any distortion, you really need you need n choose 2 dimensions. Okay?
Wait a second. So do you want to have some efficient process, or are we only talking about existence?
Yeah, currently it's just existence, but typically in all these things, it's also, like you saw in the previous slide, it's a very simple process, yeah. Right. So if we allow a little bit of distortion, if distortion is 1 plus epsilon, then turns out you can do much better. And this is due to a sequence of works by Shefman, Talagan, and recently by Newman and Rabinovich, who actually they removed an extra log factor from that term. So this is currently the best known result that says that if you want to have distortion 1 plus epsilon, the dimension needs to be only linear, which is this is much better than the square we had before, and so it's n over epsilon squared. So for distortion epsilon, you need n over epsilon squared. So it's only linear dimension, but it's not clear if this is the best you could do. Right? Remember, in the setting of L2, you could get all the way down to log n dimensions. So you might hope the same would also happen here. And I should say, as L1 is another very natural measure of distance, right? It also has lots of applications. It's another thing we would really like to have. But turns out, and this is the focus of our talk, there are low bounds. Turns out you cannot really hope to get log n dimension reduction. So it turns out that if you allow dimension d, now think of d as being big, say if I allow distortion 10, then it turns out I need at least n to the something like 1 over 100 dimensions. Okay, so we cannot hope to get log n dimensions. It has to be polynomial in n for any constant distortion d. Okay, so this is a result by Charikar and Brinkman from 2003, and a few months later, a simpler proof was found by Lee and Naor. Okay, and this tells us that there must be a certain polynomial dependence in n, but this bound turns out that when distortion is very close to 1, like you're really interested in very good embeddings, like distortion 1.1, turns out this bound cannot give you anything better than square root n. Okay, and this leads us to the last result mentioned here, and this is from just a few months ago from last Fox. This is a result by Andoni, Charikar, Naiman, and Nguyen. What they showed is this much stronger bound. They showed that if you care about distortion 1 plus epsilon, then there's this bound over there, which is essentially n to the say 0.99, so n to the 1 minus something small that decreases with epsilon. Okay? So at least for distortion close to 1, I would say there is a decent, reasonably good understanding of the problem. We know that the ballpark is around distortion n. Okay? Because we have an upper bound that's linear in n, and the lower bound is not quite linear in n, but almost there. Okay? Of course, there's a gap to be closed here. For bigger distortions, there's actually much less known. I would say there's a very big gap to close here, and there's this possibility that you might actually get sublinear distortions. We don't know yet. Maybe I don't know what the true answer is, but so this is still an open question. Anyway, the topic of today is I want to focus on these two results and show you a simpler, more intuitive proof of these two bounds. And actually, it's one proof that covers both. So I mean, hopefully after in 40 minutes you'll know how to prove both results, both for big distortion and for small distortion. It's actually almost the same proof. Definitely the same idea. Okay, and the proof is based on information theory, and I think it's somewhat intuitive. I'll try to convince you of that. If not, then let me know. Okay, and I should say, of course, I mean, I'm not reinventing everything here, right? There are existing proofs, and I'm using some of the ideas. In particular, I'm using the same matrix that they suggested. So I'm taking the same matrix and proving for those matrices that they cannot be embedded. So it's not, this part is taken, of course, from previous proofs, and the metrics these metrics are known to be. I knew the metrics are hard, so this is why I chose the same matrix. Okay. So let's go to the proof. But before I go to the proof, I should start with some introduction to information theory. And most of what I'll say is quite basic, but it's still good to refresh to have a short refresher on the definitions. What we need is basically the entropy, the conditional entropy, mutual information, and chain rules, Fanous inequality. Let's go through this. It's not that much. So we need to know what the entropy is. If we have a random variable on some domain of size little d, this little d will later become the dimension of the embedding. You see why. The entropy is simply the sum of pi log 1 over pi. Okay, so this is the entropy of the random variable. And this is always at least 0. It's easy to prove. It's always at least 0. And also easy to prove it's at most log d. Okay, so it's kind of between 0 if the random variable is kind of deterministic, if it's always the same, always obtain the same value, and it's log d when it's uniform over the domain. Okay, so conditional entropy, one way to define would be if I have two random variables, x and z, I kind of fix z, and for each z, I consider the entropy of x, and I kind of average over all fixings of z. This would be the first definition here, and it's not easy to show it's equivalent to the other expression over there. But that's kind of the entropy that x has once you already fix z on average. And there's a nice chain rule. So if you consider the entropy of x and y conditional on z, then it's the entropy of, by definition, x, y, z minus entropy of z. I'm just using the definition here, which is, again, I'm just introducing here plus entropy of xz minus entropy of xz. And you see that this now simplifies to entropy of x given z, entropy of y given xz. Okay, so this is a very simple algebra. All I'm saying is that the entropy of x and y given z is the entropy of x given z and the entropy of y given both x and z. Okay, this is somewhat.
X comma y is the same as without.
Yes, so this is a common misuse of notation. Typically in this information theory notation, you don't write the commas. I should have maybe not written any commas. But right, in principle, there should be commas here between the x and the y. Yeah, I'm sorry about that. Okay, so there's now, this is the chain rule, and it's maybe somewhat intuitive. Entropy in both x and y is you first look at the entropy of x and then look at the entropy of y, but x is already fixed. Another nice definition we'll need is the mutual information. There are several ways to define it. It's a mutual information between two random variables, x and y. It's the entropy of x minus entropy of x given y. And it's also entropy of y minus entropy of y given x. The two things are easily shown to be equal. And it kind of measures how much information there's shared between x and y in the sense that how much information x tells us about y or equivalently y tells us about x. It's always between 0 and the minimum between the entropies. So if you have two random variables and they're independent, then this would be 0 because there's no information that one gives about the other. And if they're equal, then the mutual information is simply the entropy of each of them, if they're always equal. So this is another very important definition, the mutual information between two random variables. We're almost done. The last thing we need is the conditional mutual information, which is defined as you would expect it to be defined. It's simply the one way to define it would be to average over settings of z of the mutual information between x and y, or equivalently, you can consider the entropy of x given z minus entropy of x given y z, which is just putting conditioning on z here. So this tells you how much mutual information there is between x and y when you fix z. And fixing z can change the mutual information between x and y because they're not independent. We'll see an example in the next slide. And there's also a chain rule for this, which is also easy to check. I'll leave that for you. But it says that the mutual information between y and two random variables, x1, x2, it's simply the mutual information between y and x1 plus the mutual information between y and x2, but conditional on x1. This is the most important thing in this slide. This is what we'll need later, this kind of chain rule for mutual information. Okay, so if I have one random variable y and I want to consider the mutual information with a bunch of other random variables, I can first consider how much information y gives me about x1, and then add how much information y gives me about x2, but condition on x1 that I already looked at. Okay, all these things are very easy to prove. It's just one line of algebra, but kind of to understand what it really means takes some time to get used to these intuitions. So, any questions? Okay. Soon, I hope in the next slide or two, you'll see why I'm doing this information theory 101. I also need something slightly more sophisticated, not much more sophisticated. It's a basic statement known as Faneu's inequality. All it says is that if you have, say, in this case, 2 bits, x and y, and x is a uniform bit, and y has, with high probability, y equals x, so y kind of predicts x well. All this claim does is it quantifies the mutual information between x and y. So just this claim that is essentially Faneu's inequality tells you that if x is a uniform bit and y equals x with good probability, then there's some mutual information between them, and it quantifies how much mutual information there is between x and y. Just to see why this makes sense. I mean, if y always equals x, okay? So if x is a random bit and y always equals x, we know that the mutual information between them is just 1. Okay? Because what we said before, because the entropy of each of them is 1. So that would be the extreme case when p is 1. But more generally, this inequality tells you, how much mutual information you can hope to have. Okay, so this is a very special case of Faneu's inequality. This function h of p that's plotted here, this is what's called the binary entropy function, is defined here. So this 1 minus the entropy looks like that. Okay, so this is just a way to quantify how much information y has about x if they're equal with some probability. Okay, let's just see the proof, because it's if you don't have to listen to the proof, but it's just one line of proof or maybe 2 lines of proof. So maybe you might as well just see it. The information between x and y is the entropy of x minus entropy of x conditional y. By definition, entropy of x is 1 because it's a uniform bit. So the mutual information, the thing we're trying to low bound, is 1 minus the entropy of x given y. Okay, I haven't done anything yet. And now let's look at how we actually bound this conditional entropy. So the entropy of x conditional y, and this is the trick, I introduce another random variable. It's an indicator of x equals y. Okay? So the first equality is obvious because once I fix y, the entropy of x is the same as the entropy of x together with indicator of x equals y. Right? Because when y is fixed, x is essentially in bijection with the pair x comma indicator of x equals y. And now I just use the chain rule I mentioned before. So this I can express as the entropy of the indicator condition on y plus the entropy of x condition on both. And the first guy here is at most the entropy of the indicator alone, because conditioning cannot increase the entropy. This is simply by convexity. This is easy to prove. Right? If you condition on something, it only decreases the entropy. Plus, I just left the same term as it is. And now all we have to notice is that the first term is exactly entropy of p, right, by definition, because we assume that y equals x happens probability p, or it's at most entropy of p. And the second term is a 0, because once I fix y and I fix whether x equals y, x is already fixed, right? Because if this is 1, then we know that x is y. If this is 0, then we know that x is 1 minus y. Because the second term here is simply 0. So if you didn't follow this, not a big deal. If you did it, great. This is a special case of Faneu's inequality. Faneu's inequality is actually slightly more general. It tells you that if you have, and this is the statement we'll need later, so this is something to keep in mind. X is a uniform bit, And now there is another random variable, y, that's not necessarily a bit. Y can be anything. And y tries to predict x in the sense that there's some function that, given y, tries to guess what x is. Okay? And what Fan's inequality tells us is that if y is good in predicting x, if f of y equals x with some probability p, then there must be mutual information between them. There must be at least y minus entropy of p information between x and y. Okay, now y doesn't have to be a bit, y can be anything. But if there's a way to predict x based on y, then there must be mutual information between x and y. So again, this is just a way to quantify something that's intuitively obvious, but you still need to quantify this, right? Because saying that y predicts x is not by itself enough to say how much, to say that they have mutual information. This is what allows you to do this. And this follows from the previous claim quite easily. What you need to use is something called a data processing inequality, which is just convexity. It just says that if you apply a function to a random variable, you cannot increase the mutual information. This is just convexity. It's also easy. It's very easy to prove. So we obtain that the mutual information between x and y is at least that of mutual information between x and f of y, which by the previous claim is at least 1 minus entropy of p. Okay, so the bottom line is this. This is all we have to know. All we'll have to use later, that if we have a random variable that is good in predicting a random bit, then they must have some mutual information. Okay, this quantifies the amount of mutual information, 1 minus entropy of p, p being the success probability of the prediction. Okay, everyone happy with that? Okay. Good. So now we can finally get to the main information theoretic tool that we need. It's, as I said, it's a very basic tool. It's been used before in several instances, but let me first introduce the question. So suppose we have a uniform bit string, n bit string x. So it's uniformly distributed over 0, 1 to the n. And what we'd like to do is compress it somehow. Okay? And still be able to extract x from that compression. So there are actually several ways to make sense of it. Let's start maybe with the strongest one. So the question is, can we find a function f that maps a bit string of length n to some shorter bit strings of length k, okay, with the hope of actually compressing the information. So say k is less than n over 2. And the goal is that if I give you f of x, if I give you the encoding of x, you should be able to recover x itself, say with probability 90%. Okay? So that's kind of the most basic, most naive setting. And it's easy to convince yourself this should be impossible, right? You should not be able to store n bits using n over 2 bits. Okay? And it's very easy to prove. You can prove it combinatorially. So this is kind of the basic setting, and obviously the answer is not, and it's easy to see. So a slightly maybe more interesting question is this. What happens if I just want to recover any 1 bit of x with probability 90%? So I no longer require that you should be able to give me the entire x. I just want that you can do the following. I'll ask you, give me the 10th bit of x, or give me the 11th bit of x. And you should be able to give me that bit with probability 90%. Kind of say probability taken over everything here. So maybe this is slightly less obvious if you haven't seen it before, but if you think about it for a second.
It's the same as being able to recover a string that agrees with x 90%.
Yeah. Right.
90% of entries.
Right. If you can do that, you might as well just ask for each of the bits, and then you kind of get 90% of the bits of x correctly, and that should already be impossible. You can use the error correction to recover the original string, or you can just directly argue this combinatorially. Right, so this should also be impossible, and indeed this is impossible, and it's also not so difficult to prove, right? If you can do each bit, you can also get the whole string. So okay, let's try one more thing. Let's try what happens if now I ask you, give me the 10th bit of x. Okay, so you have the encoding, you have the encoding of x. But now I ask you, give me the 10th bit of x, but I give you a hint. I also try to help you. I give you bit 1, 2, 3, up to 9. So I give you all the bits appearing before the 10th bit, and I ask you, can you tell what the 10th bit is? Okay. So what I'll show you in the next slide is this is also impossible. I think it's combinatorial. You can probably convince yourself why this should also be impossible for similar reasons. But the information theoretic argument gives you exactly the right dependence on the parameters. This is what we'll use here. And just before we proceed, another case you can consider is the following: what happens if I give you all bits but the ith bit? So I ask you, can you recover the 10th bit, but I give you all the other bits but the 10th bit? Then,
Yes.
okay, you're still awake. Then it's possible. Good, yeah. Then it's possible, and it's actually easy, right? You can just store the XOR of all the bits, and it's just one bit to store. And you know, if I ask you for the 10th bit, and I give you all the other bits, you can easily recover the 10th bit. Okay. Good. So this is what we'll focus on. This is something called I call it the random access code. And I'll mention in a minute, this has been used in several instances. It's actually a very simple argument, but it turns out to be amazingly useful. Also for dimension reduction, as we'll see in the next slide. Okay, so the setting is again the following. We have a mapping, and the mapping maps each string is 0, 1 to the n. It maps it to, now let's think of it as not 0, 1 to the k, but just let's think of it, let's just flatten it. Let's think of it as the universe 1, 2 up to d. Okay, this fits more with my notation later. And assume that you can recover any bit of my choice with probability 90%, given all the previous bits. Then the theorem says that the d has to be big, d has to be at least, say, 2 to the 0.8 n. Okay, you can actually put here the exact dependence. We'll see that from the proof. You actually get the exact dependence here. Okay. So in other words, this just formalizes what we said in the previous slide. You cannot compress the information, even if all you require to do is recover the ith bit, given the previous ones. Right, so this is actually important. This corresponds to a function f that is randomized. So I mentioned before, you can even use encodings that are randomized. So the function f doesn't have to commit to a certain encoding. It can have randomness and map a bit string x to some probability distribution over d in this case, or over 0, 1 to the k in the previous case.
But the recovery should only be based on a sample from the distribution.
Right. Of course, yeah, right. So you kind of, you get the result of the encoding. It's some specific result. Yeah, exactly. Okay, so because the proof is just one line, it looks like 3, but it's actually one line. Let's see what it is. It's actually very simple. So the idea is this: we have x being our string, our n-bit string. So x is made of x1, x2 up to xn. Each of them is a random bits. M is my encoding. So M is a random variable that lives in this universe D. So here's what I'm going to do. Consider the entropy of M. Okay. M in this case, again, is the encoding. In this case, because I don't consider X, we're essentially looking at the entropy of the average message. The entropy of M is the most log D because it lives in domain of size D. So I told you before, entropy can be at most log D. Okay. Something that lives in domain of size D. The entropy of M is clearly at least the mutual information between X and M. This is something I also mentioned before. The mutual information can never be bigger than the entropy of each of the terms. Okay. So I know that the mutual information between X and M is at most log D. And the chain rule is what completes the proof. Let's now write this mutual information between X and M in the following way. It's the mutual information between X1 and M plus the mutual information between X2 and M given X1, and so on and so forth, plus the mutual information between xn and m, given all the previous bits. And now if you stir this, what do we have here? We have a lower bound on d, lower bound on log d, in terms of the information encoded in the message about each of the individual bits, given the previous bits. And that should sound very familiar. So the only thing we need to do to complete the proof is argue that these terms are big. And the way we argue this is by saying, because we can predict x1, say, with probability 90%, there must be mutual information between them, using, say, Faneu's inequality to quantify this.
It seems like actually using mutual information makes it a little harder to understand. In that, so you could just say, look at the random variable that tells you whether your predictions are correct for every bit. Together with the compression, and this random variable is concentrated on, has expected Hamming weight 0.9, so it doesn't have, can't have more than like the h
Right.
of 0.9 times n bits of entropy. Together with the compression, this can determine x. This completely determines x. So the compression plus this string of entropy h of 0.9 times n together determine a string of length n, of a random string of length n, and so the compression must have length n minus h of 0.9 times n.
You might be losing log there. I'm not quite sure about what you're saying. If you do it quantumly, you exactly use log. Lose log. So you might be
We'll
losing
lose a log in what way?
You want somehow reduce your error. You do unit bounding over the error. So
No, I'm not doing a union bound over.
It's the
Yeah.
same proof.
It
It's
looks
the same proof. Yeah,
Yeah.
it's the same proof. It's just without using neutral information, just using entropy.
Okay, you could probably rewrite it. Yeah, chain rule, you just use a chain rule for entropy instead of mutual information. Yeah, okay.
It's probably closer to 0.5, not 0.8.
Yeah.
Because the entropy of 0.9 is pretty
Yeah.
big.
Okay. So, okay. So this is what I want you to remember, and I should say we'll need actually later a slight variant of this, and the variant is the following: the encoding is not of a bit string, but a string over alphabet 1, 2, 3, 4, and the decoding does not quite recover the number, does not recover the 1, 2, 3, 4, but only recovers the value mod 2. So only tells us if it's 1, 3 or if it's 2, 4. But turns out that exactly the same proof works there. Okay.
Isn't it even the same problem? If you just ignore
No, because what you obtain as a hint, all the 1, 2, 3, 4, so you obtain the actual values of the previous bit. So it's on the same proof. It's on the subcase of the previous one. So again, this is a setting we'll in later. The string that's being encoded is over alphabet 1, 2, 3, 4. You get all the previous digits, but you only have to predict the digits mod 2. Okay, and still the same bound holds. You need something like 2. Okay, so I said this bound actually is very useful. It's been used at least 3 different places I know of, probably elsewhere too. It's used in most, the nicest application is to obtain lower bounds on 2 query locally decodable code. This is Kiranidis and DeWolf. And it's been used elsewhere too. It's been used in lower bound gap Hamming distance and maybe some other places. So it seems like something that's quite useful, and this is the technique I'd like to encourage you to look at. So let me tell you what the proof looks like. Let's go back to our question, the question of dimension reduction. The metric we'd like to use is this. It's what I call a recursive diamond graph. So this is diamond graph. This is the basic diamond graph. And the recursive diamond graph is obtained by replacing each edge with a diamond. So this would be level 1, this n equals 1. N equals 2, it looks like that. Okay, so I replaced each edge by another diamond graph. Okay, so if you do this n steps, you obtain a graph with something like 4 to the n vertices. Okay, you can figure out the exact number. It's a nice exercise, but it's something like 4 to the n. Okay. And it turns out, this is one fact we'll use, is that this graph, or I should say the shortest distance metric on the graph is known to be in L1. So you can, what I have here is the embedding into L1. So let me convince you it's really an embedding. Consider any edge, and you'll see the distance along this edge in L1 between, this is the point 0, 0, 0, 0. Okay, this is the point 0, 0, 1, 0. The distance here is 1. Here distance is 1. Distance is 1. And distance from here to here, distance is 2. Distance from here to here also distance is 2, right? Because they're different 2 locations. So the L1 distance corresponds to distances in this graph. This is an embedding of this graph into L1. Okay, I was hoping to get some comment here, but no guy. Okay, so it's not quite an embedding into L1, but yeah, it's kind of almost.
Not to scale.
No, it's just not an embedding into L1. You can see, take the distance from here to here. The distance is 2. It should be 4, right? So 1, 2, 3, 4. But that's not a problem. Yeah. So this is not actually this graph, this shortest path metric is not embeddable into L1. It's not a problem because the thing we're actually showing a lower bound for is this embedding I showed you here. The metric given, not this embedding, but the metric given by these points. Okay? So the metric we actually obtain is going to have distances that are slightly different from the ones shown in this graph. But the only important thing is that distances along edges and along what I'll use as cross edges are fine. Okay? This is the only thing I'll use about this metric. So kind of long range distances might be slightly different, but it's not going to bother us because we'll never use those distances. Okay? So the lower bound is actually for the metric shown here and not for the graph itself, but it's not a problem. Okay.
Is it a tree metric? Or?
It's an L1 metric. So it's
this
not.
is a subset of the
Yeah.
cube, of the four-dimensional cube. with,
Yes, right.
what is missing?
So no, so in general, right, in general it's going to be, let's see.
Deleted edges, right? So then
So, no, so
mismatch.
this is confusing. When you do n recursions,
1001.
it's going to be 2 to the n dimensional, right? But you're only going to have 4 to the n points. So it's a very specific subset of the hypercube. Kind of in 2, it seems like it's, right, but bigger n, it's a very sparse subset of the hypercube.
Any L1 matrix you can
Right,
make in
right.
in some cube.
Right, so L1 is always a combination of cut metrics, and yeah, and this is also the kind of explicit way to show it, to present it as a cut metric. Okay, so this is the metric we'd like to work with. So just forget about, just think of the graph as what we'd like to show a lower bound for, even though this graph is just not in L1, but it's not going to cause any trouble because we're using the metric that was shown there. Okay, so here's how and this is one kind of one-line summary of the bound. This is all you have to kind of the message you want to take back from this talk. So assume we have an embedding of the graph into L1D. Okay, and what I'd like to show you that D has to be big. I'd like to show that you cannot have an embedding into low dimensions. Okay.
By the graph, you mean this funny metric?
Yeah, I mean you can ignore the subtlety there. You can by the graph I mean the set of points of this graph. It's just that the distances that you have among these points are not quite those shown in the graph. Okay, but for distances I'll use actually match the distances in the graph. Okay. So assume, just for simplicity to illustrate the idea, assume for simplicity there's really no distortion. So assume we have a mapping of these points of the graph, of the vertices of the graph into L1 to the D, and assume there's no distortion. So let's see what happens. I'd like to orient the edges of the graph from left to right, so I can meaningfully talk about the head and the tail of the edge. So all the edges are going from left to right. And if you think about this, what happens now is that each edge, so remember, each point is mapped to a point in L1 to the D. Right? This is an embedding. But now each edge is now mapped to a vector, the difference between the head and the tail, a vector in R to the D, whose L1 norm is exactly 1. Okay? Because we assume we have an embedding into L1. Okay? So because the distance on this edge is 1, it should be embedded into a vector in L1 to the D whose norm is 1. Okay? And here comes the main idea. You have an embedding here into a vector that sums to 1. So you might say that the edge is mapped to a probability distribution. Okay, so you want to think of this embedding as associating a probability distribution with each edge. Okay, so what I did here, so we can talk about the edges, I want to label them. So the labeling goes like that. The first digit tells you where you are in the kind of the high level, in the first level of the recursion, and then the second digit tells you where you are inside. So it's kind of cyclical 1, 2, 3, 4. Okay, so it's 1, 1, 1, 2, 1, 3, 1, 4, and here it's 2, 1, 2, 2, 2, 3, 2, 4, and so on. So let me summarize what I said. if we need to assume that each edge is mapped to a non-negative vector. I'll later justify why we can do that. But if you grant me that, if you're willing to believe that each edge is mapped to a non-negative vector, then what we have here is really that each edge is mapped to a probability distribution over D, right? Because it's mapped to a vector whose L1 norm is 1, meaning the sum of the coordinates is 1. Okay? And if it's also a non-negative vector, then it's really probability distribution. And this is the main idea. So we can think of the embedding as providing us with an encoding of the edges. Each edge is mapped to a probability distribution over D. Okay? And now why is that embedding useful? Why the embedding, why are we interested in this embedding? And this is the main observation, okay? So you consider the embedding of the edge 1, 1. So this is 1, 1 here. So f of 1, 1 is a probability distribution. Think of f 1, 1 as being a probability distribution, okay? Consider the embedding of f 1, 3. Add them together, divide by 2, and take the difference, between the thing here. So this is kind of the mixture of the two distributions, 1, 1 and 1, 3, and this is the mixture between 1, 2 and 1, 4. We're taking the difference and taking the L1 norm. So what we're doing here is considering the statistical distance between these two distributions. Okay? And I claim that this L1 norm is 1, and to see why, you have to observe this. So what we did here is the following. This is f of 1, 1, this vector here. F of 1, 3 is this vector here. F of 1, 2 is kind of going backwards from right to left, this vector here. And f of 1, 4, or minus f of 1, 4, goes also backwards from right to left. So this expression here inside the norm is essentially the vector here, right? Essentially the vector going from here to here. And because we assume this embedding has no distortion, we know that this vector must belong. So this vector must be of length 2, but I divide here by a factor 2, so I get the norm is 1. Okay, so what I'm saying is that because we have an embedding of this graph, we know that the following, this equality must hold. Okay, so this kind of combination of the probability distributions has norm 1, and if you interpret this in a probabilistic way, it tells you that this probability distribution written here, which is simply the equal average of 1, 1, and 1, 3, has statistical distance 1, and complete disjoint from the average of 1, 2, and 1, 4.
Sorry, is there a factor of 2 missing? F14 plus minus F14 plus F11 is already the vector, right?
So
you get 2 copies of the vector.
Right, but I divide here by 2.
But the length of this vector should be 2.
The length is 2, right? So okay, so right. So the expression inside the norm is this vector, and yeah, I think it's okay. And I divide by 2 and I get 1. Okay. Good. So what we have here is that these two distributions, meaning the average of 1, 1, 1, 3, is disjoint from the other distribution, from the average of 1, 2, 1, 4. And what it tells us is that we can easily tell them apart because they are disjoint. They have statistical distance of 1. Okay, the variational distance between them is 1. So we can easily tell them apart, the two distributions. In other words, we can perfectly distinguish the encoding of 1, 1 and 1, 3 from 1, 2, and 1, 4. Okay? And if you recall, this is exactly the task that we had to do in random access codes. Right? We're given an encoding, and we're supposed to recover the second digit of the encoding, right? Given the first digit. So we already know that the first digit, say, is 1, and we're supposed to detect the second digits, but only mod 2. I mentioned this before. I only need a second digit mod 2. Okay, and of course, you can do this with any of the other 4 components, right? It doesn't have to be 1. It would be equally good if the first digit is 2 or 3 or 4. So what we've seen here so far is that if there's no distortion, we can recover the second digit mod 2 given the first digit. So we can recover the second digit mod 2 given the first digit. Let's also see what happens with the first digit. So we can similarly recover the first digit mod 2. And for this, we just use other edges. So let's define these edges of the level 1 recursion. It's the same proof, just in a higher level of the recursion. So this is F1, this is F2, this is F4, and this is F3. So the same edges kind of one level back in the recursion. And just write down, you see that we have the same kind of equality. Now it's using this anti-diagonal edge. And again, it has to be of norm at most 1, at exactly 1, which tells us that we can exactly distinguish 1, 3 from 2, 4. Okay, so we can exactly predict the first bit. So this is essentially the proof. I mean, the main idea is just to think of it as an encoding and then use the random access code to say that the dimension must be big, because you cannot have such a encoding that allows you to decode the bits given previous bits. You should not be able to do that unless the dimension is big. Okay, so to summarize, when there's no distortion, this is the simple case we did here, but you'll see the proof is the same when there is distortion. It's not a big difference. So when there's no distortion, we obtain an encoding of 0, 1, 3, 4 to the n into some universe of size d that allows us to decode any coordinate mode 2 given all the previous digits. So, which gives us that d has to be at least 2 to the n, which is essentially square root of the number of vertices. Okay, because if you recall, there is 4 to the n vertices in this recursive diamond graph. Okay. So when there's no distortion, we obtain a lower bound of square root number of vertices on the dimension. Okay. And if there is some distortion, you just have to do the math. So in case there is distortion, capital D, what we obtain here, because this cross edge is not really of length 1, but of length, it might be shorter, okay, because of some distortion. This cross edge might turn out to become of length 1 over d. We're only able to distinguish with the bias 1 over d. So it's just the same equality as before holds, but now it's not perfect distinguishing. We can only distinguish with some bias. So the probability of correct decoding is slightly more than half. It's half plus 1 over 2d. Okay, just because the edge, this cross edge is not 1. Yeah. Right, the statistical distance is not 1, but now it's 1 over d. And because statistical distance is 1 over d, this is the bias I can get in prediction. And then you just have to plug it into Finance inequality, and this is what you get. You get the information that you have on each bit is 1 minus entropy of half plus 1 over 2d. This entropy you get from Finance inequality. You know how much entropy this prediction gives you. And we obtain, hence, the dimension lower bound of, the dimension must be at least 2 to this expression times n, which is, capital N to the 1 over d squared. So it's exactly, we recover exactly the same asymptotics and perhaps even similar constants to Charika-Brinkman and Linauer. This is the result for high distortion.
In the distortion case, do you also lose the fact that the edge is a probability distribution? I mean, they have the sum of the coordinates is exactly 1. Then the interpretation is probability distribution.
Okay, I'll mention this later. So I kind of try to hide here is the fact that we are no longer dealing with distributions, but also kind of sub-distributions, because they're not, the edges themselves might not be of norm 1, but it's not a problem. You'll see later why. Okay, so just to give you a hint, just to show you how this extends, this is what's known as the recursive cycle graph. This was introduced by Andoni, Charika, Naiman, and Nguyen a few months ago. And then what they do is say, because the previous graph, as you saw the previous graph, the best lower bound we could obtain is square root number of vertices. Okay, even if there's no distortion whatsoever, the best lower bound we could get is the square root number of vertices. And for a good reason, because the graph, if you recall at the beginning, I showed you that there's a way to embed it in 2 to the n dimension. So the graph is perfectly, it lives in dimension 2 to the n. So it's no wonder we couldn't prove a better lower bound. But their idea is to kind of use slightly more sophisticated graphs. Instead of using diamonds, they use cycles. In this case, it's a 6 cycle, but you should use, in general, slightly longer cycles. The reason this works is because of the following reason. The number of vertices behaves now like 2k to the n. Okay, in this case, k equals 3. So the cycles are of length 2k. So number of vertices is 2k to the n. But, and again, it's in L1 if you do it properly. And, I should have said that. So number of vertices is 2k to the n. But the amount of information you get, what you're able to predict k different letters. So the reason taking k to be bigger than 2 helps you is because the number of vertices behaves like 2k to the n, but the number of strings you can decode behaves like k to the n. So if you compare the two expressions, you have a better polynomial dependency. It's no longer square root. Okay, so it's 2k to the n versus k to the n. Let me just show you quickly why this happens, but it's a very similar proof. There's one thing maybe you have to worry about, but it's more or less the same. It is the same intuition. Now we take one of these cycles, and now we consider two cross edges, the one here and the one here, and we just write down the expressions that correspond to them. And what they tell us is that, at least in the case where there's no distortion, it tells us that we can distinguish kind of 1, 4, 2, 5 from 3, 6. This would be this edge here. And it tells us also we can distinguish 1, 4 from 2, 5, 3, 6. And if you combine the two, it tells you can really distinguish 1, 4 from 2, 5 from 3, 6. Okay, this is in the case when there's no distortion. So it kind of allows you to work with alphabet of size 6 and predict the value mode 3. You can tell apart 1, 4, 2, 5, and 3, 6, all three options. And at least when there's no distortion, you get a dimension lower bound of k to the n, okay, because we predict k different things. So it's k to the n, which has much better polynomial dependency on number of vertices, because number of vertices is only 2k to the n. Okay? And so I won't show you the exact calculation, but turns out that when distortion is 1 plus epsilon, if you do it carefully and plug it into Fanus inequality, this is one thing you need to observe here, how to go from this to a good reconstruction of the bit, but it's not too difficult. And you get a dimensional bound of this form, which is exactly the kind of expression we wanted to have. You just have to plug in an optimized choice of k, the length of the cycles, and you get exactly n to the 1 minus 1 over log 1 over epsilon, which is the same expression that showed up in the work by Andoni et al. So we really recover the same kind of lower bound. Okay, so there's one remaining issue, which is how to make sure that the vectors are really of L1 norm 1. I cheated a bit because when there's distortion, the vectors might be a bit shorter, and also how do you make sure they're non-negative, which maybe seems like a more serious issue. But turns out it's actually surprisingly easy maybe to deal with both issues. What you can do, you can just, if you have a vector that does not sum to 1 and maybe has negative coordinates, what you do, you separate into the positive part, so this is 0.2, 0, and 0.4, and into the negative part, this is it, 0, 0.30, and if it still doesn't sum to 1, just add another coordinate that makes it sum to 1. So it's kind of an easy reduction to the case we saw before. You have to make sure it all works out, but this simple tricks does the job. So even if you have an embedding that doesn't quite work, you can slightly massage it, and then you get vectors that are truly probability distributions. Kind of intuitively, the reason this works is because if the vectors are shorter, you only lose, because what you're trying to do is make this cross edge long, and if your vectors themselves are short, you don't gain anything. So you might as well do that. And also, negative coordinates don't seem to buy you much. So this is a simple reduction to the case we showed before. Just how to deal with the case where the embedding does not quite give you probability distributions because it maps to vectors that are shorter than 1. So they don't sum to 1, but sum to 0.8. Okay, so let's keep that. And so the conclusion is, if you care about that, I think that because the proof is information theoretic, maybe this relates to Russell's question before. Because the proof is information theoretic, it automatically extends to what's known as quantum information, which is simply embeddings into matrices, not into vectors. I don't know why this is a natural question, but the proof gives that kind of for free. So if you ever care about embedding of graphs into matrices, this gives you the same kind of lower bound. Distances are now distances if you consider the eigenvalues. So if the distance between two matrices is you subtract them, then take the sum of the absolute values of the eigenvalues. So
is there a natural thing in quantum?
Yes. This is statistical distance. This would be the statistical distance in quantum. Yeah. You just look at the eigenvalues and sum the absolute values of the eigenvalues. Yeah. But yeah. So so they are not necessarily. So let's think. Yeah, Hermitian. So I assume the embedding is to Hermitian matrices, right? it might work also with non-Hermitian. Like you can do, you can reduce it maybe to the case of Hermitian, but I don't know. Yeah, I think at least the proof I have in mind should work for the Hermitian case.
So this trick about the negative and positive and so on doesn't matter then?
Right. So it should be okay. Yeah. But yeah, I mean, it's maybe something to check more carefully. I didn't write it down because I don't see any clear applications for this, but yeah, I think this should work out. I think the main, so open questions, of course, for me, the interesting question is to find other applications of this trick. And of course, in terms of dimension reduction, I mean, can you close this gap? There's a big gap here. What happens when distortion is some big distortion, D, say 10? You know, can you reduce dimension to below linear? This would be very, very nice if you can find dimension reduction going below n. It seems very difficult question, so maybe the right answer is actually low bound, but we still don't know the right graphs, the right kind of metrics that would show such a low bound, because the metrics we currently have don't seem useful for that, because the bounds we showed here are tight, so you really need, or somewhat tight, you really need new metrics. Okay, that's all. Thanks.
Do you get some meaningful strengthening if you try to use the direct product statement for random interscope?
I'm not sure what's there, I mean, where one can improve here, because the low bounds are somewhat tight, so
is there no
you might use these intuitions to come up with other metrics that would have better distortion. Yeah, this is the bottleneck currently, to find the right metric.
So what is known for LP is close to 1 but not 1?
This you should ask, Moses or I don't know.
Actually, their low bound, the linear works with the norm close to 1, right? And then
The linear,
the
yeah.
linear simplification of
Yeah.
the,
Yeah, but it has to
so
be,
they actually have a bound.
yeah, but it has to be very close to 1. So I don't think there's a good bound for LP for P fixed, say P 1.1. Yeah, it gives you some constant, but it's not asymptotic. Yeah, so if I take this with a grain of salt, but I don't think there's much known.
Also, your bound also L2 squared, so that's not like the same thing.
Yeah, I'm not sure, because the metric is.
Squared, so it just has you like root of that squared.
It might, yeah. Yeah. We'd have to make sure that the reductions work, but yeah. Yeah.
So, what happens if you start with graphs other than cycles? And do you get some general?
Yeah, so the hope is maybe once you have this intuition on why this works, maybe you could easily come up with other graphs. We tried a bit, but it's not. Yeah, it's not doomed.
Yeah, they have to be.
Right. Right. So it's not clear how you can do something kind of more efficient than cycle. But yeah, but it's definitely a possibility. It's good.
Do you know how efficiently random graphs can be?
Random graphs, but you want something that's in L1. You want something in L1, so you want to choose some random subset of L1.
The cube, say.
Do you want to choose a cube and try to reduce? No, but the cube is already in low dimensions, already in log n dimensions.
I mean, these were subsets of the cube.
But very, very sparse.
Random subsets of random.
Every N1 thing is a subset.
Yeah, but
But you need a sparse subset.
Yeah, so maybe random. Yeah, random sparse subset of L1.
But then
Yeah.
probably all distances are about the same. If it's a random subset.
Then you're in this almost Euclidean range, aren't you?
Yeah. Right. So you're saying this distance is sparse, but the actually interesting distance is happening here. Right. Good. Yeah. Right.
More questions?
Okay.
Yeah, Joe.
So in those examples you gave where you sort of have you have these n random bits and then you have in some sense a set of test questions where you sort of say, we will give you this much information and
Right.
then you have to predict. bit with probability 90%. Is there like a mechanical way, to given such a list of things, to figure out how much the device needs to be?
You mean different sets, families?
Yeah,
There are extensions of this, to other settings. I think Shear's lemma, is that the right term? Yeah. So, this is for the sequential case, but I think there are some extensions for other settings. I give you that amount of information, you have to recover that bit. I guess there are several ways you can imagine this could be extended.
The thing is that is it even known to be computable?
I don't know. Yeah.
That the last thing, the parity case, but is there some mechanical means where you would just sort of an algorithm that is computing how much you would need?
Right. So this is a bit similar to the setting in this broadcast. Yeah. So maybe this is the extension you have in mind. Okay. I have to think about this.
Thanks a lot.
Okay. Thanks.